All right, we're going to begin by taking a look at the extra credit that you had an opportunity to complete over the weekend, page 175, word problem 32. Did anyone attempt word problem 32? All right, disappointed, but let's take a look at it now then, except now we don't get any points for it. Go ahead and read the word problem if you would, Maddie, nice and loud. All right, so we're working with two-digit number word problems, and Maddie, I said there's three things we need to remember. First of all, as we write a two-digit number, we need to remember that the tens digit should simply be represented, and the other digit in a two-digit number, of course, we call the units digit, and we would represent that U. And then we said that the number itself should be written, I'm sorry? 10t plus u, because the value of the tens digit is always 10 times its own self, right? So this is stuff we'd all covered. So when it says in the opening sentence, Maddie, that the sum of the digits of a two-digit number is 13, we could write that, right, the sum of the actual digits, not the number, but the digits of the number, is 13. The first equation's super easy. And then it says, if the number is written in reverse, well, give me an example of a two-digit number, Maddie, any two-digit number. What? You're evil, Maddie. Because you know darn well, if we reverse the digits of 11, we're right back at 11. Okay, I was like, there's no way. There's no way with all the two-digit numbers out there that she's going to pick something where the digits are the same. So I even thought about qualifying my statement when I said it, and I was like, nah, the odds are so astronomically against, never mind. All right, how about one where the digits are different? 14. All right, so Maddie, 14, this digit has a value of 4, and this digit has a value of, it does not have a value of 1. It has a value of 10. Now it is a 1, but it has a value of 10, right? And 10 plus 14, or plus 4 gives us 14. If we reverse the digits, what would the number become? 41. Where now this digit has a value of 1. The old tens digit is no longer worth 10 times itself, it's just worth itself. And this 4 now has a value of, that is to say that what was the units digit now has a value of 10 times itself, right? So, U3, how do you suppose we could write a number, 10t plus u, in reverse? Realizing that that which had a value of itself would now have a value of 10 times itself, and that which had a value of 10 times itself would now only have a value equal unto itself. How do we represent a two-digit number again, Maddie? So t had a value of 10 times itself, and u just had a value of itself. So if we reverse the digits, 10u plus t. Does that make sense? That's how we would write a reversed two-digit number. Again, that which was only worth 4 now has to be worth 4d. That which was worth 10 now only has the value of 1, for instance. So it says if the digits of a two-digit number are reversed, or if the number is written in reverse, then this reverse number is, class, equals 9 more than the original number. How do you suppose we represent 9 more than the original number? Brecken? Good, 10t plus u plus 9. And that was the system we were going for on the extra credit. Obviously, none of us tried it, so none of us had it. Gavin, if you tried it, I'd be very interested to hear if you got this. Does it make sense now how to set this up? All right, at your seats, solve. At your seats, solve. Yes, sir.
I tried it. I just got nowhere near the right answer.
All right, but does it make sense now? Good. I'm glad you at least tried it. Well, I'm curious, what did you put for the reversed digits?
U plus 10t.
I got it. And you see that that would reverse the kind of the direction, but it doesn't actually change the value, does it?
Yeah, multiply instead of that.
Oh, instead of 9 more than, you did 9 times. Okay. All right, I appreciate you giving it a try. No one else in the class gave it a try. Good job, Brecken. Just for that, you can have all the confetti from my floor that you want. No charge. Stuff it all in Noah and Maddie's lockers. Just kidding. Y'all keep your lockers locked, now you're here. Yeah, Brecken standing out there patiently sliding it through the slots one piece at a time. You can't lock me out.
Staying after school just so I can do it.
Pencils down, look up this way. Let's see how we were doing here. I took this and I said, you know what, let me just bring all the t's and u's over here. So I brought the 10t over as a negative 10t to get negative 9t. I brought u over as a negative u to get 9u, and I got 9u minus 9t equals 9. That's just begging me to knock a 9 out of everything, right? U minus t equals 1. I then took this, and because addition's commutative, I flipped them. U plus t equals 13, right? No reason I can't do that. Cancel the t's, t equals 14, u equals 7, plug that back in, t plus 7 is 13, so t is 6, and the number 67. How many on the right track? How many made it harder than it had to be and saw that this way is super easy? All right, questions? Now let's check it. We said that the number is 67, but according to the problem, the sum of the digits should be 13. Yeah, that's how I got the 6, right? So I can't use that as a check, I've got to use the other one. If the digits are reversed, what would the number become, class? 76. Would 76 be 9 more than 67? Yes, it would, and it checks out. So that's what we should have had for the extra credit. Any questions on that? All right, well, let's get back to what we were talking about last time. Turn back to page 284, where the rest of your homework was. And we begin talking about this concept of similar or like radicals. And we said, what is it that would make radicals similar? There's 2 requirements for radicals to be similar to each other. Bracken? Same index and? Same radicand. Class, what are the 2 requirements for similar radicals? Same index, same radicand. And if radicals have the same index, same radicand, then they are similar. And just like you can add like terms in algebra, you can also add or subtract like or similar radicals. And we add them the same way, right? Just like with adding like terms. You only really add or subtract the coefficients. You leave the letter portion alone. Well, same here. We're going to leave the radical portion alone and only add the coefficients. You did numbers 13 to 33, the odd for homework. Excellent. And bueno. All right, let's go and take a look at this and see how we did. Number 13 was really straightforward. They were already written similar to each other. 8 times the square root of 3 plus 6 times the square root of 3 minus 7 times the square root of 3 equals, Noah? 7 times the square root of 3. Couldn't be easier. Number 15 is kind of weird because they are similar radicals. They're still square roots of 3 like the last problem. But one's a 5 square root of 3, and then you're supposed to subtract a 7x times the square root of 3. What did you get for your answer, Maddie? Good. Negative 7x positive 5 times the square root of 3. Now, one little thing I would say here, Maddie, you went ahead and put them in descending order, which I do like. My only problem is you led with a negative, and it's been a little while since we talked about this. But remember we said in a polynomial we never want a negative first term. So we should go ahead, if we're going to do it this way, factor out the negative to get 7x negative 5 times the square root of 3. Or, to be honest, I'm actually cool with this, since we're not doing anything else with the problem anyway. I would have been okay with this answer. So technically these are all correct. Technically these are the better written answers. How many had at least one of those though? At least one of them. All right, good. You're not going to see a whole lot of problems like this anyway, so I'm not going to sweat that too badly. Number 17, they are not all like radicals. But each radical does have a buddy that's like to it, if you will. And Brecken, what did you get for your answer here? Good. 6 times the 5th root of 3 plus 2 times the 5th root of 2. How many had 13, 15, 17, all three correct? Okay, good. We're off to a good start. Now, number 19 is where things start to get dicey, because these radicals are not similar. At least they don't appear to be similar to each other. And you can't just add these all together the way they're written, right? We've got to do what first to get them similar, Noah? Right, to reduce the way we've been doing for over a week now, let's factor it up. But remember my strategy tip was, find the easiest one, Brecken, and if you'll factor that one up, that'll give you a clue on how the other ones should turn out. So, Noah, which of these did you feel like, man, I got this. I know exactly how to reduce this one. Which one? Which of these three radicals do you see the factors of very quickly? The 27, all right? And you said, I see that the 27 would factor into times 9, where you could take the square root of the, to get, times the negative 3 that was already here. And then once you've reduced that one, your hope, class, and it's not always going to work out this way, but your hope is that maybe 75 can factor into 3 times something. Can it? Ah, okay, that works out great, because we can take the square root of 25 to get times the 4 that was already there. And it'd be really nice, wouldn't it, know if this also came out to a 3 times something. Three goes into 4. With 1 left over, 3 goes into 18. Ah, and that works out. Now, 19 would have been depressing, wouldn't it? But 16 works out great, doesn't it? Because we can take the square root of the 16 to get times the 5 that was already here. Times the square root of the... And now we can add them together. 20 times the square root of 3 plus another 20 times the square root of 3 minus 9 times the square root of 3 should have given us 31 times the square root of 3. How many had this answer? I'm guessing Noah did not. You did. Good question.
I wrote down 3 for the negative 9, and then I tried to write like a 9 over it. I guess I didn't read it right. I just subtracted 3.
Gotcha. So you end up with the 37 times the square root of 3? All right, so just little things there that we can be careful of in the future. Number 21, back to one where they're all similar to each other, though they're not all like terms to each other. Brecken, what did you end up with for your answer on number 21? Times the square root of 3y? Okay, good. So we saw that the negative 6x has no friends, right? But the 9 square root of 3y and the 1 square root of 3y combined to give us a positive 10. And then all of that times the square root of 3y, just kind of factoring out the 3y. Same thing I said to Maddie earlier, I would factor out the negative here. In fact, if you wanted to, you factor out a negative 2. If you're going to do any factoring at all, you might as well. Though again, you don't have to. Or write the positive first, then put the negative 6x after it with the square root of the 3y, because again, we're not doing anything else with it anyway. How many have one of those answers for number 21? All right, question? Okay, careful. Yeah, so the 9 would combine with the 1. The negative 6x doesn't have any other x's, x squared of 3y's to combine with. Number 23. You can't combine them all together, but you can combine some of them, Maddie. Good. The 7 squared of 2 has no friends, but you can combine the square root of 6's to get 4 times the square root of 6. So, as Maddie said, 7 times the square root of 2 plus 4 times the square root of 6. Number 25, same thing. A couple of them can combine and then one of them can't. Noah, your answer? Good. Or I like to put the positive one first. 5 times the cube root of 2x and negative 3 times the cube root of x, but it doesn't matter. Okay. Them being out of order is not a problem here. Number 30 or 27 is kind of an interesting one here. So let's take a look at this together, bracket. We've got a 3x times the square root of 2 plus a 4 times the square root of 8 minus a 2 times the square root of 2x squared. None of these are similar right now. Can we factor this at all? We can't do a thing with it. So the 3x times the square root of 2 is just going to have to stay the way it is. What about this? Can we factor that at all? How can you factor an 8? Where we can take the square root of the, to get, times the 4 that was already there. All right, so now again, they're not like terms because they don't both have x's, but they are at least like radicals. Let's come over here now. I can't factor the 2, but maybe there's something I can do here with the x squared. All right, pull an x out. 2 goes into 2 one time with nothing left. So we end up with, there we go. And so, hey, now we've got a couple terms that are not only similar radicals, but actually like terms that combine very easily. And then the 8 times the square root of 2, again, is a like radical, but not a like term. However, here at the end, we could essentially factor out the square root of 2. There we go. We would just put the square root of 2 at the back end instead of the front end as we factor it. Did anyone get this answer? X plus 8 times the square root of 2. Okay, great job, Maddie. Gentlemen, questions? Does it make sense now? All right. Let's see, that was kind of a weird one. Number 29, I think, is back to a little bit more normal. Maddie, let me come to you here because I gave Noah the last one that was like this. Got the square root of 8 plus the square root of 98 plus the square root of 72. And again, Maddie, my recommendation always is start with the easiest one because that could guide your thinking on the more complicated radicals. So hopefully you started by reducing the square root of 8, factored it into where you ended up with. Then the clue class is, what do we want for our other two radicals? 2. Maddie, they're both even numbers. They will factor with a 2. The question is, do we end up with squares, right? And when we divide the 98 by 2, we factor it into a, that works out well because that becomes, how about the 72? That works out great also. And sure enough, we can add them all together to get, and we have this answer on number 29. Excellent. Looking at number 31, I got a 3x times the square root of 20x plus the square root of 80x cubed minus x times the square root of 45x. No, I'm going to go ahead and come to you on this one. Again, none of them are similar right now. We're going to have to reduce all of the radicals down. Which one do you want to start with? All right. And of course the x, don't want to lose the x. Which of those things, what do we do with those different things? Take the square root of the 4, right, to get 2. Is there anything else we can do with the 5x? All right, so what do we reduce all of this to? There we go. All right, let's come here, or maybe here. Maybe let's come over here. Thoughts on the, because that looks easier to me. How might we factor up the 45x? And of course the x, and of course we can take the square root of the, all right, so that gives us Hey, and that's a similar term and a similar radical, both. How about up here with the 80? Yeah, both of these came out to 5s, and of course the 16 works out great for us. So we take the square root of the 16 to get 4, and we'll leave the 5. What can we do about the x cubed? I'm sorry?
You take the 2 over 3.
2 goes into 3 with, there we go. So we can reduce that down to a 4x times the square root of 5x, and now they all combine together to give us? How many have that answer on number 31? Questions on number 31? Okay, if these were individual radicals, I think we would have been just fine. So when they're all put together in the same problem, don't let it throw you off. You're still just reducing radicals like we've been doing the past week. Same song, second verse, you just add them up when you get to the end. Questions on 31? And number 33, we come to Brecken, where we've got a 5 minus the square root of 28 minus the square root of 63. Obviously the 5 kind of just standalone rational value. Let's address the radicals now, though.
Negative 2 times the square root of 7, and then negative 3 times the square root of 7, and then we get 5, negative 5 times the square root of 7.
Great job, and those don't combine anymore because that is not a square root of 7. Don't try to combine it with the others, only those two combine. Great job, Brecken. How many of the same answer? 5 minus 5 times the square root of 7? Question, Noah. Does it make sense now, what we're doing? All right, again, with the homework, the goal is do your best, see how you do. We go over it. The objective is that by the time we're done going over it, you understand it better than you did before you started the homework. Any questions at all? All right, let's do a few more of these together here. You can set your books aside for a few minutes. Just have your notes out. And again, for the third or fourth time this hour, I'll say it again. Essentially, an addition of radical problem is really just reducing radicals. You just have 2, 3, or 4, or 5, or 6 of them all at the same time to do. Where each one used to be its own problem, now we put lots of problems all together and make it harder. Except that you can use the easy one to help you on the hard ones. Write this down if you would. 2 times the square root of 8 plus 6 times the square root of a half minus the 6th root of 8. On the surface, this is a mess. Really what this is all 3 reducing methods in the same problem. Method number 1 for reducing radicals, normal method for reducing radicals, class, is that when you see a radical of a fairly sizable number, you try to do what to the number? Factor it, right? So let's do that with the 8. Let's factor the 8 into 2 times 4, where we take the square root of the, to get a 2 times the 2 that was already out here. 4 times the square root of 2. Right, no big deal there. We did that in the homework. We come to the second radical, and we see a fraction. That changes the game plan, because for a fraction, it's not about factoring. For a fraction class, it's all about taking the root of the denominator. Good, Brecken did it without looking at the bulletin board. Take the root of the denominator. And you can't. Yeah, we can't take the square root of 2. Darn. Thoughts? Okay, if you were to multiply top and bottom by a 2, you could make this become a square root of 2/4, couldn't you? By the way, I want to show you something. When you have a coefficient in front of a fractional radical, write the coefficient over 1. Go ahead and do that at your seats as well. Let's write the coefficient over 1. You're going to see why here in just a moment. Because now I can do what Brecken said. I can take the root of the denominator, Brecken. What do I have here now? In the denominator, just a 2. What about the numerator? The square root of 2, right? You can't take the square of the numerator, but remember, I don't care. I can take the square of the denominator. That's all I care about. Now remember, this is 6 over 1 times the square root of 2 over 2. And remember, with multiplying fractions, we said we can cancel a numerator with a denominator. So seeing it this way will help you remember the 2 and 6 can actually cancel, class, to give me 3 and 1. And now my only denominator is a 1. I don't really care about that. So I'm going to write this as 4 times the square root of 2 plus, this essentially becomes, class, 3 times the square root of 2. Now be careful. Don't fall for the trap of saying, oh, let's just take half of 6. No, that's not how it works. There's a progression here, okay? But if you'll follow the steps through, there we go. That worked out well. Now we come here. And I've got a really big index, right? Square roots we're cool with, cube roots we're cool with, 6th roots not so much. So remember, our third method of reducing radicals, class, is to make the index smaller. But the only way to do that is to rewrite the radicand as a power. How can I rewrite 8, Maddie? 2 cubed. And now that I can see that exponent, what can I do, Maddie? To get, so really this whole thing just becomes negative square root of 2. Or we could say negative 1 square root of 2 if we wanted to go and write a coefficient there. And now, class, that which was a fractional radical and a whole number radical and a 6th root that comes out of nowhere all becomes similar, and we get what for our answer, class? 6 times the square root of 2. Questions on this? Do we see how we could actually work through potentially all three reducing methods rather in the same problem? Questions? Not every problem will be like that, of course. Write this one down if you would. The cube root of 192 plus the square root of 80 minus 4 times the square root of 45 plus 5 times the cube root of 24. Can I add these the way they're written, Noah? Why not? What's the word we're looking for? You might have just said it. Maybe I just didn't hear you. They're not, class, similar. Okay, there we go. No, they're not similar to each other. In fact, while none of them have the same radicand, they also, class, don't all have the same index. Do we see that there's no way these two are going to be similar to each other? But maybe this one could be made similar to, class, the last one, the cube root of 24. Maybe, if we reduce them down. Maybe the second one could be made similar to the third one, because they're both at least square roots. So here I'm not looking to try to make them all similar, but let me look at these two cube roots, because those possibly could be made similar. And let's start with the easy one, huh? Which one's the easy one, the first one or the last one, Brecken? I think the last one's a whole lot easier. Now remember, it's a cube root. So I'm thinking of cubes right now. How might we factor a 24? Eight times 3. Not 4 times 6. That'd be for a square root, but 8 times 3. Good. And Brecken, of course, we'll take the cube root of the, to get, which we'll multiply by the 5 to end up with. Now realize, class, I'm not interested in a 3 right here. That's a square root. It's not going to be similar anyway. I'm not interested in a 3 right here, which is good, because I know 3 didn't go into 80. But that doesn't matter. This one maybe could be made similar if I could factor it into 3 times something. Somebody besides Brecken, 3 times what would give me 192? 64. Can I take the cube root of a 64, class? What is it? 4. Good. The square root would be 8, but the cube root would be 4. So what do I wind up with here, Noah? All right, so those two cube roots, yes, indeed, did become similar to each other. They didn't start out that way, but they ended up that way. These two are not going to be similar to those, but maybe they could be similar to each other. Maddie, which of those radicals looks easier to you? The 45? How might we factor a 45? Well, I can take the square root of the, to get times the 4 gives me. All right. Maybe then, this could have a square root of 5. Anyone factored in 5 times? I'm sorry, that's incorrect. 16? So what do I end up with here, Brecken? And sure enough, these two are similar, and these two are similar. So Noah, what's our answer going to be? A little bit louder so I can hear, please.
-8 times square root of 5. Positive 14 times the cube root of 3.
There we go. -8 times the square root of 5, positive 14 times the square root of 3. Questions on that problem? Let me give you some to try on your own now. We'll start with an easier one, I think. Square root of 28 minus square root of 63 plus the square root of 700. When you're done with that, move on to the next 2 problems. Maddie's finished. Pencils down. Pencils down. Now, if you were watching on YouTube just now, or maybe Maddie was able to watch while I was doing this since she was finished, you kind of see how the brain ticks in the order in which I approach these. I started with the easiest one, which in this case was the very first one. 4 times 7, 2 squared is 7. I immediately saw 7 times 9, so negative 3 squared is 7. And then, oh, that's easy too. 7 times 100. 10 squared is 7. Combined them all to get 9 times the square root of 7. Felt that first one was pretty easy. Did we all get that answer? All right. Looking at the next one, I kind of looked at it for a second. I went straight to the 20. 4 times 5, pull out the 2, negative 8 squared root of 5. Then I looked at this, I was like, no, 5 doesn't go into that. Again, over here, I was like, 5 does go in, but that's 5 times 15. Now, your brain may take a little longer to get there, but it ain't going to work either. I was like, well, 5 goes into that. What's that? Let's see, 121. And again, you're probably going to take a little longer than I did, but that's because I'm the math teacher. But again, you should get there. 11 times the square root of 5 comes out pretty nicely. Then I came back to this, like, well, I know it's not a 5. Oh, duh, 25 times 3. Negative 5 square root of 3. Well, in that case, maybe there's a 3 over here, because I knew there wasn't a 5. Yep, 49. And again, you may take a little longer to get there than I would, but that's okay. 7 times the square root of 3. You'll combine your square roots of 3, combine your square roots of 5, and there's your answer. Did you get 2 times the square root of 3 plus 3 times the square root of 5? Good question. Of the 4, how many did you correctly reduce down? 3 of the 4. Which one did you miss? The 75. Did you do 15 times 5? And then you're like, now what? Right? Because you can't do anything with that. So that's where it's like, okay, something different's got to work here. Now, I will give you credit. You got 49 times 3. That's not one I would have seen as quickly. I saw it because I got the 25 times 3, and that 3 kind of helped me out over here. So, now, were you still working on this one when I called time? Or had you just kind of moved on? All right, so when the 15 times 5 didn't work, you should have used the 3 as well. Maybe it goes with the 3 one then instead of the 5 ones, because there's a couple with 5s. Maybe this is one of the ones with a 3. Maybe that should have helped you. All right? Do you understand a little bit more how to think them through? Okay, let's take a look at the last one then. And I looked at it for a second, and then I wound up over here. 54's got to be the easiest number, right? So I'm like, 8. Nope. 27. Yeah, there it is, 27 times 2. Pull out a 3, negative 3, cube root of 2. I'm like, come on here. Let's come to the 128. Does 2 work? 64. Yes, okay. Maybe the 2 works again. Sure enough, 343, there's the 7 times the cube root of 2. Ended up with 8 times the cube root of 2. How many had that on the last one? I guess Maddie's the only one who finished. You didn't get that? All right. You were working on it. Were you on the right track? All right, so everything you did on that problem was correct, just didn't finish. How about you? You said you were working on it.
I started with 128, so it took me longer.
Yeah. Find the easy one. Do you see how if you'll start with the easy one, it'll guide everything else? All right. But you were on the right track. Okay. Maddie, where was your mistake then? Oh, you did 9 times 6, which for a square root, 9 times 6 is perfect. But it was a cube root, so 9 doesn't do us any good, right? All right, so now, were the other 2 correctly done? Or did you try to use like a 6 time, well, 6 wouldn't work on either one, would it? So these 2 were correct, and just that one was not so much. Did you end up with 3 times the cube root of 6? You said the cube root of 9 was 3? All right, questions on that? All right, you're going to get some practice with this in your homework this evening. You're also going to do a couple word problems for homework this evening. Page 288. Page 288. Need you to do the review, numbers 5 through 12. Page 288. The review, numbers 5 through 12. Then on page 289, do word problem 16. Page 289, do word problem 16. And page 182, do word problem 15. Page 182, so we're going to go back 100 pages, word problem 15. So a couple word problems involving systems of equations. They're not 2-digit number problems, but they will involve systems of equations similar to problems that we've been working recently. All right, we'll take a look at that tomorrow. Also plan for a quiz tomorrow over adding radicals. Plan for a quiz tomorrow over adding radicals. So as you do your homework tonight, do it to the very best of your ability. Put the time and effort in so that way between homework and us going over it tomorrow, you'll be ready for that quiz. Have a wonderful rest of your day, and you are dismissed when the bell rings.